Before we talk about sharing, let us first understand what a control loop is. A control loop is a small job that keeps running continuously in a loop. It looks at a part of the cluster, compares what is happening with what and should be happening, and asks Kubernetes to correct any difference. And it keeps on doing the same thing over and over again. For example, a replica set control loop may see that 3 pods are desired, but only 2 are running. It asks the API server to create one more pod. On its next check, it sees 3 running pods, so no further action is needed. The loop keeps watching because the cluster can change again at any time. A controller process is the running program. Inside it, one or more control loops can focus on different responsibilities. Several of those loops may still need the same pod information. That brings us to the question for this episode. Should every loop perform its own list, watch, cache, and recovery? Why does Kubernetes need more than one control loop? Because the cluster is not trying to solve just one problem. It must keep the right number of pods running, notice unhealthy nodes, track jobs until they finish, update service backends, and handle many other responsibilities. One large loop could try to do all of this, but it would quickly become difficult to understand, change, and recover. Kubernetes uses smaller, focused loops instead. Each loop watches a limited part of the cluster and makes one kind of decision. The loops can run at different speeds, retry independently, and change without turning the entire control plane into one large program. These loops are separate because their responsibilities are separate, but the information they need can overlap. The replica set loop needs pods to count replicas. The node loop needs pods to understand which workloads are affected by a node problem. The job loop needs pods to know which tasks completed or failed. And the endpoint slice loop needs pod readiness when building service backends. So several focused loops may all need the same changing pod data. Now let us focus on 3 loops inside one controller process. The replica loop keeps the desired number of pods running. The node health loop reacts when a node problem affects those pods. The policy loop checks whether each pod follows the required rules. They solve different problems, but all 3 need to know when pods are created, changed, or deleted. The most direct design is to give every loop its own watcher. Each one sends a list request, downloads the same starting pods, opens a separate watch, builds its own cache, and implements its own recovery path. It works, but the observation work is repeated. Now imagine 3 control loops all asking for the same pod information. Each one downloads the same list, listens to the same changes, and keeps its own copy in memory. If the connection breaks, each loop also has to recover on its own. So Kubernetes ends up doing the same work 3 times, even though all 3 loops are looking at the same pods. The better design separates 2 jobs. First, observe the pods and maintain a trustworthy local view. Second, let each control loop decide what that pod change means for its own responsibility. Observation can be shared even when the decisions remain independent. Now let's talk about the shared informer architecture. A shared informer is not just one component. It is the complete mechanism that keeps a shared local view of Kubernetes objects. The reflector talks to the API server and receives the initial list and later changes. Those changes are used to update the local indexer, which stores the latest objects. The shared processor then tells all registered handlers that something has changed. So the reflector collects the information, the indexer remembers it, and the shared processor distributes it. Together, they form the shared informer. When the informer starts, the reflector first asks for a complete list of pods. The response contains the pods that exist at that moment and a resource version for the snapshot. In this example, the snapshot is version 500. The informer applies that initial snapshot to its local indexer. Before the controllers start making decisions, they wait until this initial synchronization is complete. Otherwise, an empty or half-built cache could be mistaken for the real cluster state. Once the cache is synchronized, the control loops can read pods through local listers. A lister searches the shared indexer in memory, so several controllers can inspect the same current pod view without sending repeated GET or LIST requests to the API server. After the initial list, the reflector opens OneWatch SIA from resource version 500. The API server now sends only the changes that happen after that snapshot. One upstream stream is enough to keep the shared local view moving forward. Suppose pod B is updated at version 501. The event travels through the reflector, the informer applies it to the indexer, and the local resource version moves forward. The controllers do not each repeat this update. The shared store changes once. Once the local store is updated, the shared processor tells all registered handlers that something has changed. This happens inside the same process, so the handlers do not need their own separate watch connections. Kubernetes watches the change once and then shares that update with all the interested handlers. The same pod change can mean different things to different control loops. The replica loop may decide that pod B needs to be checked again. The node health loop may see no problem and do nothing. The policy loop may check whether the pod still follows the required rules. They all receive the same update, but each one responds in its own way. There is another useful point to note here. The event callback tells the controller that something has changed, and when the controller is ready to reconcile that, it can read the latest version of that object from the shared cache. This will be required because several updates may arrive while the controller is still busy with earlier work. The informer also centralizes recovery. If the watch connection breaks, the reflector first tries to resume from the last resource version. If that history has expired, it performs one fresh list and rebuilds the shared cache. The local controllers here, of course, do not each run their own recovery against the API server. The local cache is quick to read, but it is only a nearby copy of the cluster state. Because updates reach it after they pass through the API server, it may be slightly behind for a short time. Controllers can use the cache to understand what is happening, but every create, update, or delete must still go through the API server. And when a controller needs to confirm that a recent change has really been accepted, it should check through the API server instead of assuming the cache is already up to date. A shared informer is not shared across the entire Kubernetes cluster. It is shared only by control loops running inside the same process and watching the same type of resource in the same scope. For example, pod watchers can share one pod informer, but deployments need a separate informer. And if the controllers run in different processes, each process creates and maintains its own informer. A well-behaved controller process also starts these pieces in the right order. It registers handlers, starts the informer, waits for the initial cache to synchronize, and only then starts worker loops that depend on the cache. During shutdown, the shared stop signal closes the informer and its workers together. The transformation is now clear. Before, every consumer maintained its own list, watch, cache, and recovery. Afterward, one shared informer maintains the upstream view, while many controllers reuse local reads and local notifications. The engineering idea behind the shared informer is simple. When several consumers need the same changing data, do not make each one repeat the expensive observation. Maintain one recoverable local view. Then let every consumer apply its own logic to that shared view. But sharing the stream creates the next problem. Pod changes may arrive faster than a controller can reconcile them. The same pod may also change several times while it is already waiting to be processed. How does Kubernetes buffer those changes, preserve the important order, and avoid scheduling the same key again and again?